In the past few videos, we've been building all of the terminology and tools necessary to find all of the local extreme values and saddle points to a surface. So z equals 3x minus x cubed minus 2y squared plus y to the fourth was an example from one of the earlier videos from the very first one where we visually inspected it to find the locations of mins and maxes. You can also visually find locations of saddle points on that graph. In this video, we're going to use the second derivative test for local extreme values to find out where those local extreme values and saddle points really are. So I know I might need to find all the first partials and all the second ordered partials. So my first partial with respect to x, I just differentiate everything with respect to x and I get 3 minus 3x squared. My first partial with respect to y, minus 4y plus 4y squared, cubed. That's important. Now I need to set both of these equations equal to 0. I could factor out a 3. And we could do some arithmetic. I'm going to factor. And from that factoring, I see that x is plus or minus 1. So literally any point where x was equal to plus or minus 1 would give me 0 as the 0 for the first partial with respect to x. Of course, I want to know the points where both of these are 0 at the same time. So let's set this one equal to 0 and hope that we can find those points. Well, let's factor again. So I could factor out a 4 of this. So I could actually factor out a 4y. So again, a little more factoring. And from this equation, I see that y could be 0 or plus or minus 1. So what I have to do now is pair each x with each possible y. And the reason for that is that this equation only depended on x and this equation only depended on y. So by writing a 1 in the x coordinate, I've automatically zeroed this one out. Well, there are 3 different ways to zero this one out with these numbers. So I have 1, 0, 1, 1, and 1, minus 1, all as critical points. Now, I have to do the same thing for minus 1. Minus 1, 0 is a critical point. Minus 1, 1, and minus 1, minus 1. All of these are critical points. So let's write those out. So minus 1, minus 1, minus 1, 0, minus 1, 1, and 1, minus 1, 1, 0, and 1, 1. Those are my critical points. I want to calculate my second ordered partials, and then we'll need to calculate some specific values for some of those second order partials and the discriminant. All right, so from our previous work, fx, the first partial with respect to x was minus 3x squared. First partial with respect to y was minus 4y plus 4y cubed. Second partial with respect to x would be minus 6x. With respect to y, would be minus 4 plus 12y squared. And a mixed partial. Well, there are no y's here, so that's 0. And of course, this one has to be 0 too then. This one, I'm pointing at a first partial. If I take the second partial with respect to y and then x, I would also get 0 because of Clairaut's theorem. So my discriminant is the expression minus 6x times minus 4 plus 12y squared minus 0, because my mixed partials were 0. Okay, so I need to plug all my critical points into this to find out if I get a positive or a negative. I also need to plug them all into this. I suppose if I get less than 0 for my discriminant, I actually don't have to worry about this, but I'm just going to build a big table where I find f(x)(x) at each one of these critical points and the value of the discriminant at each one of those critical points. Right, just setting up a very large table of things. Here I'm going to find f(x)(x) at each one of these, and that was given by the equation minus 6x. And then I need to calculate the discriminant, which for convenience I'll just call d, which was minus 6x times minus 4y, minus 4 plus 12y squared. All right. I suppose if I wanted to shorten my work, I'd actually just fill in this column first. And anywhere I get something less than 0, I could skip calculating this, because if I get less than 0 for the discriminant, I know I'm dealing with a saddle point. But I'm just going to go on and fill in this column and fill in this column because I feel like it, and because this comes really easy to fill in because I'm just taking minus 6 and multiplying it by either minus 1 or positive 1. So I'm not really working that hard to fill in that column, and now I need to fill in all of these, and I might have to calculate them all, but why don't you pause the video and just go on and fill in that column so that you're a little bit less bored and maybe you just skip over me doing it. Okay, so I'm going to fill in this. Hopefully I get it all right, because I have to plug in an x and a y. So let's see, I'll have a 6 times and a minus 4 plus 12. Well, nicely enough, that's a minus 4 plus 12 is 8, is 48. All I really care about is that is larger than 0. All right, so now this one. Minus 1, well, that's going to give me a 6 times minus 4. All right, so I didn't even need to know this value because this is going to be the location of a saddle point. All right, minus 1, positive 1. Well, that's going to give me that 6 times 8 is 48 again. At 1 minus 1, let's see, that's going to be a minus 6 times. And if I think about it, it doesn't really matter what happens in here, right? Because that's going to be a 12, and it's going to give me that minus 48 this time. So again, here's a saddle point. 1 and then 0 goes in for y. Positive 24 this time. And I think I see the pattern filling in this table, but I'm just going to go on and keep calculating them. Minus 6 times 8 is minus 48. All right, so anywhere I have a less than 0, I'll have a saddle point. Okay, so I have 3 saddle points, and that's good because visually that's what I see in the diagram in GeoGebra. And my saddle points are at minus 1, 0, comma something, 1, minus 1, comma something, and 1, 1, comma something. And the reason I'm saying comma something is because a saddle point is a point on the surface. I need to calculate my z values, which means I need to look at my original function and go from there, which you can do now. The original function was z equals 3x minus x cubed minus 2y squared plus y to the fourth. And when I plug in 1, 1, I get out a 1. When I plug in 1 minus 1, let's see, I actually don't have that one written down to cheat with, so I have to do that one now. So I have 3 minus 1 is 2. Let's just write that down. I'm plugging in a minus 1. Well, both of these are even, so minus 2 plus 1 is 1. If I plug in a minus 1 and a 0, I actually get out minus 2. So there are the locations of my saddle points. In the GeoGebra graph, those are points B, C, and D, respectively. So I've handled 3 of the 6 things. I have 1, 2, 3 to go. And this is where I have to look at this column where I computed the second partial with respect to x. Anywhere I have the discriminant is bigger than 0, I can look at this to decide what shape I would have. Well, this is a positive second derivative. That corresponds to that concave upwards shape. This is going to be the location of a min. This too will be the location of a min. And then where I have the discriminant being positive and the value of xfxx is less than 0, that corresponds to that concave down shape where I'd have a max. So locations of mins and a location of a max. To find the corresponding values that are actually the minimum and the max, we actually plug these points into our function, and what we find is that there is a local minimum of minus 3 at both the points minus 1, 1 and minus 1, minus 1. It just so happens that both of these critical points have the same local min. If I plugged in these points and got at a different z value, I have to make 2 different statements, right? Because you could have more than one local minimum. There's a local max of 2 at the point 1, 0. And we can actually see that in the GeoGebra app that is posted below.